Space is not a place of chaos. From the inside, it looks like it should be overwhelming. Billions of galaxies, each containing hundreds of billions of stars, all moving apart at speeds proportional to their distance, embedded in a dark matter scaffolding 10 times more massive than everything you can see, governed by laws of physics so precise that a calculation made in one corner of the universe applies equally in a corner 13 billion light years away. And yet, to stand beneath the night sky is not overwhelming, it is calming. It is the most reliable and unchanging backdrop that has ever existed for the small, warm, temporary thing that is a human life. Tonight, the universe wants to help you sleep, and it has an extraordinary collection of facts to share. Take a slow breath in and out. The room you are in is quiet, your body is still, and up above you, through the ceiling and the clouds and the atmosphere and the magnetosphere, through the millions of miles of interplanetary space and the vast distances between the stars, the universe is doing what it has always done, quietly, systematically, patiently, continuing to exist. Everything that was here last night is here tonight. The stars have barely moved. The galaxies are in the same positions they were in when your parents were born, when their parents were born, when the first human beings looked up at the night sky tens of thousands of years ago and felt the same quiet wonder you are feeling right now. Space is almost completely silent. Sound requires a medium through which to travel, a fluid or solid whose molecules can be compressed and rarefied by a passing wave. In the interstellar medium, the gas between the stars, the density is so low that a sound wave at human audible frequencies would be attenuated to nothing in less than the width of a room. The only sounds in space are those occurring in sufficiently dense environments. The roar of plasma in the sun's convection zone, the pressure waves propagating through the intergalactic medium in galaxy clusters, the extraordinary infrasonic rumble detected by astronomers in the Perseus galaxy cluster in 2003, whose sound waves have a period of 10 million years. The lowest note ever detected anywhere in the universe, a B-flat 57 octaves below middle C. In the space between galaxies, there is only silence, a perfect, deep, absolute silence that no human being has ever experienced and perhaps never will. The speed of light is 299,792,458 meters per second. This is not an approximation. Since 1983, this number has been the definition of the meter itself. The meter is defined as the distance light travels in exactly 1 divided by 299,792,458 of a second. The speed of light is the ultimate speed limit of the universe, encoded into the structure of space-time by the equations of special relativity. Nothing with mass can reach it. The closer you approach it, the more energy is required for further acceleration, and the increase in energy required approaches infinity as your speed approaches the speed of light. This is not a technological limitation. It is a fundamental feature of how space and time work. At the speed of light, something remarkable happens to time. A photon of light, from its own perspective, experiences no time at all between its emission and its absorption. The photon emitted by a distant galaxy 10 billion years ago, traveling for 10 billion years to reach a telescope on Earth, has experienced zero time during that journey. For the photon, emission and absorption are the same moment. It is only from the perspective of external observers that the photon has been traveling for 10 billion years. Time, in relativity, is not a universal backdrop against which events occur. It is a property of observers, and it runs at different rates depending on velocity and the strength of the gravitational field. One of the most remarkable facts about the night sky is that you are never looking at the present. The light entering your eyes was emitted at some point in the past, and the more distant the object, the further into the past you are looking. The moon you see is the moon as it was 1.3 seconds ago. The sun is 8 minutes and 20 seconds in the past. The nearest star to the sun, Proxima Centauri, appears as it was 4.24 years ago. The Andromeda Galaxy, the furthest object visible to the naked eye on a dark night, is appearing to you as it was 2.5 million years ago, before any member of the genus Homo existed on Earth. And the most distant objects visible to our best telescopes are showing us the universe as it was less than 500 million years after the Big Bang, when it was less than 4% of its current age. The sky is a time machine. Every direction you look is a different window into the past. Let your breathing slow a little. There is no hurry. You are safe, and you are still, and the universe is unfolding all around you at its own patient pace. The cosmic microwave background is the oldest light in the universe, the afterglow of the Big Bang itself. Before the universe was about 380,000 years old, it was too hot for electrons and protons to combine into neutral atoms. Any atom that formed was immediately ionized again by the intense thermal radiation. During this epoch, the universe was opaque, like the interior of a star. The photons could not travel freely, but were constantly scattered by the sea of free electrons. Then, at 380,000 years, the universe had cooled sufficiently for electrons and protons to combine and stay combined. The fog lifted. The universe became transparent for the first time, and the light that had been trapped in the fog was suddenly free to travel in every direction. That light is still traveling. It has been traveling for 8 billion years, cooling as the universe expanded. Its wavelength stretched from the visible and infrared into the microwave band. Today it arrives from every direction in the sky with a temperature of precisely 2.725 Kelvin, just 2.725 degrees above absolute zero. It is the coldest and oldest light you can detect. It was the first light that existed in the universe, and it has been crossing the expanding cosmos ever since, a message from the very beginning of time. Black holes are among the most misunderstood objects in the universe. They are not cosmic vacuum cleaners, sucking up everything around them. They are objects with such intense gravitational fields that within a certain radius, called the event horizon, the escape velocity exceeds the speed of light. Outside the event horizon, everything behaves according to normal gravitational physics. If you replace the sun with a black hole of the same mass, the Earth and all the planets would continue in their current orbits, unchanged. The black hole would simply be a very compact, very dark object at the center of the solar system. The event horizon of a black hole is not a physical surface. There is no wall or membrane at the event horizon. An astronaut falling into a sufficiently massive black hole would cross the event horizon without noticing anything unusual at that moment. From the outside, however, the astronaut would appear to slow down, their signals redshifting to longer and longer wavelengths, their image growing dimmer and more reddened until it asymptotically approaches the horizon but never quite crosses it from the external observer's perspective. The infalling astronaut and the outside observer have genuinely incompatible descriptions of the same event. Both are correct within their own reference frames. The largest black holes known are the ultramassive black holes at the centers of the most massive galaxies. Tone 618, a quasar in the constellation Canes Venatici, is powered by a black hole with a mass of approximately 66 billion solar masses. Its event horizon has a radius of about 200 billion kilometers, roughly 1,300 times the distance from Earth to the Sun. The entire solar system, out to the orbit of Neptune, would fit within the event horizon of Ton 619, with room to spare. If you replaced our Sun with Ton 619, the black hole's event horizon would extend far beyond the Kuiper belt, past the heliopause into the Oort cloud. Neutron stars are the densest objects in the universe with a physical surface. When a massive star, between about 8 and 20 solar masses, exhausts its fuel and undergoes a supernova explosion, the core collapses under its own gravity. If the remaining core mass is less than about 2 to 3 solar masses, the collapse is halted by neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed into the same quantum state. The result is a neutron star, an object with a mass of 1 to 2 solar masses compressed into a sphere about 20 kilometers in diameter. A neutron star is so dense that a teaspoon of neutron star material would weigh approximately 10 million tons on Earth. The surface gravity of a neutron star is approximately 100 billion times Earth's surface gravity. If you dropped a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with an energy equivalent to approximately 1,000 hydrogen bombs. Mountains on neutron stars are at most a few centimeters tall before they collapse under the gravitational field. The entire surface of a neutron star is essentially perfectly smooth by astronomical standards, deformed only by the extreme forces of its rapid rotation and powerful magnetic field. Let your body be completely still now. Let your hands rest open. The neutron stars are out there right now, spinning in the dark, their lighthouses of radio emission sweeping across the galaxy. The black holes are there, patient and calm. The microwave background is arriving from every direction, the faintest possible whisper of the universe's beginning. And you are here, on a small rocky planet in the outer third of an ordinary spiral galaxy, wrapped in a thin layer of atmosphere, breathing slowly, drifting towards sleep. The Voyager 1 spacecraft is the most distant human-made object in existence. Launched on September 5th, 1977, it is currently more than 23 billion kilometers from the Sun, moving at about 17 kilometers per second relative to the Sun. It crossed the heliopause, the boundary between the Sun's sphere of influence and interstellar space, in 2012, becoming the first human-made object to enter interstellar space. The signals from Voyager 1 travel at the speed of light and take more than 22 hours to reach Earth. When Voyager 1 was launched, personal computers did not yet exist. The integrated circuits aboard Voyager 1 contain approximately 3,500 transistors. The phone in your pocket contains approximately 16 billion. Voyager 1 carries a golden record, a copper disc plated with gold and designed to last for 1 billion years in the vacuum of space. It contains sounds and images of Earth, greetings in 55 languages, music from Bach to Chuck Berry to Indian classical ragas, the sounds of wind and rain and surf, the cries of birds and whales, a mother's first words to her newborn child. The record was assembled under the supervision of Carl Sagan, and it is humanity's most deliberate and considered message to whoever might find it, now or in the far future. Voyager 1 will drift through interstellar space for the rest of cosmic time. In about 40,000 years, it will approach a nearby star. In the very far future, billions of years from now, it will still exist, carrying its golden record through the dim, dying galaxy. Gravitational waves were predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. He was highly skeptical that they would ever be detected, because the distortions they produce in spacetime are extraordinarily small for any astrophysical source accessible to earthly instruments. He was proved spectacularly wrong on September 14, 2015, when the LIGO observatories in Livingston, Louisiana and Hanford, Washington simultaneously detected a gravitational wave signal lasting less than a second. Analysis of the signal revealed that it was produced by the merger of two black holes, one with a mass of approximately 36 solar masses and the other about 29 solar masses, at a distance of about 1.3 billion light years. The peak power of the gravitational waves emitted during the final milliseconds of the merger was approximately 3.6 times the combined luminosity of all the stars in the observable universe. The distortion produced by this cataclysm, after traveling 1.3 billion light years, was a change in the length of LIGO's 4-kilometer arms by approximately 4 times 10 to the negative 18 meters. This is 1/10,000th the diameter of a proton. The LIGO detectors are sensitive enough to detect changes in length at this scale by comparing the travel times of laser beams bouncing back and forth along the two arms, whose interference pattern shifts detectably when the arm lengths are unequal by even this extraordinary tiny amount. It is one of the most precise measurements ever made by any instrument in human history. Space is not empty. Even the most perfect vacuum possible, a region containing not a single atom, is nevertheless not nothing. Quantum mechanics predicts that the vacuum is filled with zero-point energy, a residual energy that cannot be removed even at absolute zero temperature. Virtual particle-antiparticle pairs constantly pop into existence and annihilate within the time permitted by the Heisenberg uncertainty principle. The vacuum is a seething sea of quantum fluctuations. This is not a theoretical speculation, it has direct observational consequences. The Casimir effect, observed since 1948, is a force between two uncharged metal plates placed very close together in vacuum, caused by the difference in quantum vacuum fluctuations inside and outside the gap between them. The effect is small but real and measurable. The quantum vacuum is also thought to be responsible for one of the most important phenomena in cosmology, Hawking radiation. In 1974, Stephen Hawking proposed that near the event horizon of a black hole, the intense gravitational field causes virtual particle pairs to behave differently from normal vacuum pairs. Occasionally, one member of the pair falls inside the event horizon while the other escapes to infinity. The escaping particle carries energy away from the black hole, causing the black hole to slowly lose mass. For stellar mass black holes, the radiation is undetectably small, but for very small black holes, the effect dominates and they evaporate rapidly. In the far future of the universe, when all other sources of energy have been exhausted, the last black holes will slowly evaporate through Hawking radiation, one of the final processes of the aging cosmos. Exoplanets, planets orbiting stars other than the Sun, were first confirmed in the 1990s. Before that, there was no direct evidence that planets existed outside our solar system, though it seemed reasonable to assume they did. As of 2024, more than 5,600 exoplanets have been confirmed, and statistical analyses of the data from the Kepler Space Telescope suggest that virtually every star in the Milky Way hosts at least one planet. The galaxy contains an estimated 1 trillion planets. Among the most intriguing exoplanets discovered so far are the TRAPPIST-1 planets. The TRAPPIST-1 system, located about 40 light-years from Earth in the constellation Aquarius, contains 7 known Earth-sized planets orbiting an ultra-cool red dwarf star. 3 of the 7 planets, TRAPPIST-1, F, and G, lie within the star's habitable zone, the range of distances at which liquid water could exist on the planetary surface. All 7 planets orbit within a distance smaller than Mercury's orbit around the Sun, and they are in a remarkable gravitational resonance with each other. Their orbital periods locked into simple integer ratios. If you stood on any one of the TRAPPIST-1 planets, the other 6 would be visible as disks in the sky, some appearing larger than our moon appears from Earth. Proxima b is another fascinating case, a planet orbiting Proxima Centauri, the nearest star to the Sun, at a distance of only 4.24 light-years. It has a mass roughly similar to Earth and orbits within the habitable zone of its star. Whether it is actually habitable is unknown. Proxima Centauri is a red dwarf prone to intense stellar flares, and any planet in its habitable zone would be much closer to its star than Earth is to the Sun, potentially being tidally locked with one face permanently toward the star and one face permanently away. But the fact that our nearest stellar neighbor may have a rocky, potentially habitable world is a remarkable fact to contemplate as you drift towards sleep. Let your thoughts drift gently. The exoplanets are out there, enormous numbers of them, circling their stars in silence. Some have oceans, some have atmospheres, some have weather systems and seasons and tides. We do not know yet which of them, if any, have life, but the chemical building blocks of life, the amino acids and nucleobases and sugars that make up DNA and proteins, have been found in meteorites and in molecular clouds. They form spontaneously in conditions common throughout the interstellar medium. The universe seems to have been practicing chemistry for a very long time. The night sky, as seen from space, is simultaneously more and less spectacular than the night sky as seen from Earth. More spectacular because there is no atmosphere to blur the stars. They shine as perfect, unwavering points of light with no twinkling, each one a different color clearly visible. Less spectacular in a strange way because the sky is always black. From orbit, with the sun shining directly, the sky is still black in every direction except toward the sun. There is no scattering of light without an atmosphere. Space is simply black with stars, one side in blazing sunlight and the other in absolute darkness. No gradation, no twilight, no soft blue of a scattering sky. The twinkling of stars seen from Earth is caused by atmospheric turbulence as starlight passes through the layers of Earth's atmosphere. It is refracted by pockets of air at different temperatures and densities, causing the apparent position and brightness of the star to fluctuate rapidly. This is called scintillation. The same atmospheric layers that make stars twinkle also limit the resolution of ground-based telescopes, which is why the Hubble Space Telescope, despite its modest 2.4-meter mirror, produced images of extraordinary sharpness that ground-based telescopes with much larger mirrors could not match before the advent of adaptive optic systems. Adaptive optic systems use a deformable mirror controlled by a computer to compensate for atmospheric distortion in real time. A laser beam is fired upward to create an artificial guide star in the upper atmosphere, and the distortion of this artificial star's image is measured several hundred times per second. The deformable mirror then adjusts its shape to cancel the measured distortion, allowing the telescope to produce images approaching the theoretical diffraction limit set by the size of its mirror. Modern adaptive optics systems on the world's largest telescopes can achieve angular resolutions comparable to the Hubble Space Telescope, and in some cases better. The International Space Station orbits Earth at an altitude of approximately 400 kilometers, completing one orbit every 92 minutes. This means astronauts aboard the ICE experience 16 sunrises and 16 sunsets every 24 hours. At the orbital velocity required to maintain this altitude, about 7.66 kilometers per second, the centripetal acceleration of the circular orbit exactly equals the gravitational acceleration of Earth at that altitude. This is the phenomenon of weightlessness. The astronauts are not beyond Earth's gravity, which at 400 kilometers altitude is still about 88% of its surface value. They are in a perpetual free fall, falling toward Earth, but moving sideways fast enough that they continuously miss it. The experience of living in microgravity has profound effects on the human body. Without the constant mechanical loading from gravity, bones lose density at a rate of about 1 to 2% per month. Muscles atrophy without the constant work of supporting the body's weight. Fluids shift toward the upper body, creating the characteristic puffy face and thin legs seen in photos of astronauts in space. The heart, which on Earth works against gravity to pump blood upward, adapts to the easier conditions in space and begins to shrink, losing muscle mass in a way that has to be carefully counteracted with exercise. These physiological changes are among the major challenges for long-duration spaceflight, including any future mission to Mars. The aurora borealis and aurora australis, the northern and southern lights, are produced by the interaction of charged particles from the sun with Earth's magnetic field and upper atmosphere. During periods of intense solar activity, the sun emits streams of energetic particles in events called coronal mass ejections, or in the continuous flow of the solar wind. When these particles reach Earth, the magnetic field channels them toward the polar regions, where they enter the atmosphere at altitudes of 100 to 300 kilometers and collide with molecules of oxygen and nitrogen. These collisions excite the molecules to higher energy states, and when they relax back to lower states, they emit the characteristic colors of the aurora: green from oxygen at about 100 kilometers altitude, red from oxygen at higher altitudes, and blue and purple from nitrogen. The aurora can extend across the sky in curtains and rays and spirals that dance and shift within minutes. The most intense geomagnetic storms can extend the visibility of the aurora to latitudes far from the poles. The Carrington event of 1859, the most intense geomagnetic storm in recorded history, produced auroras visible at tropical latitudes around the world, including Cuba, Jamaica, and Hawaii. Telegraph operators reported that their equipment was producing sparks and operating without the usual batteries, driven by the geomagnetically induced currents. A Carrington scale event today would cause catastrophic damage to modern electrical infrastructure, including power grids, communications satellites, and GPS systems. Such events are estimated to occur roughly once per century, making this one of the most significant natural hazard risks facing modern civilization. Let your breathing be slow and even. The aurora is dancing somewhere in the polar sky right now, whether you are awake to see it or not. Solar wind particles are channeled toward the poles and enter the atmosphere with their characteristic glow. The magnetosphere extends tens of thousands of kilometers into space, an invisible bubble of magnetic field protecting you from the radiation of the solar wind. Without it, the solar wind would strip away Earth's atmosphere over geological timescales, as it did to Mars billions of years ago when Mars lost its global magnetic field. The cosmic web is the large-scale structure of the universe, the arrangement of matter on the very largest scales. Surveys of the positions of millions of galaxies reveal that they are not distributed uniformly, but are arranged in a vast three-dimensional network of filaments and walls with galaxy clusters at the nodes where filaments intersect and enormous voids between them. The Sloan Digital Sky Survey, which mapped hundreds of millions of galaxies, revealed this structure in extraordinary detail. Individual voids in the cosmic web can be hundreds of millions of light years across, regions containing very few galaxies and very little matter. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, spans approximately 10 billion light-years in its largest dimension, roughly 1/10 the diameter of the observable universe. The cosmic web is not static. The filaments continue to funnel material from the voids toward the clusters, feeding the continued growth of galaxy clusters. The voids continue to expand, evacuated of matter that flows toward the filaments and clusters. Dark energy, the mysterious repulsive energy of the vacuum, accelerates the expansion of the universe and acts to smooth out the cosmic web over the very long term by making it harder for gravity to continue growing the large-scale structure. In the far future, as dark energy dominates increasingly, the galaxy clusters will grow ever more isolated, the cosmic web will fade, and the universe will become progressively emptier and darker on the largest scales. Saturn's rings are one of the most beautiful and scientifically remarkable features in the solar system. Spanning from about 7,000 kilometers to about 80,000 kilometers above Saturn's equator, they are composed of billions of particles of water ice ranging in size from tiny grains to chunks the size of houses, despite their enormous lateral extent. The rings are extraordinarily thin. In most places, they are only about 10 meters thick, less than 10 stories of a building. If you scaled the rings to the size of a sheet of paper, 1/10 of a millimeter thick, the paper would need to be about 2.5 kilometers across, roughly the size of a small town. A structure that thin and wide is structurally almost impossible on Earth, but is maintained in space by the combined gravitational forces of Saturn and its moons. The rings of Saturn are geologically young by planetary standards. Evidence from the Cassini mission suggests they formed somewhere between 10 million and 100 million years ago, meaning they arose long after the dinosaurs had already evolved on Earth. Before the rings formed, Saturn would have looked very different from how it appears today, more like Jupiter. The rings may eventually disappear. Material from the rings is continuously pulled inward by Saturn's magnetic field and rains down onto the planet's atmosphere. The current ring system, if maintained at its current rate of mass loss, would completely disappear in about 100 million years. We may be living in an unusually fortunate era to have such beautiful rings to observe. Jupiter's Great Red Spot is a storm that has been continuously observed since at least 1665, making it the longest-lasting known storm in the solar system. At its largest historical extent, the spot was 3 times the diameter of Earth. It has been shrinking over the past century and a half. In the mid-1800s, it was observed to be about 40,000 kilometers across, while today it is approximately 13 to 15,000 kilometers across. At its current rate of shrinkage, some scientists have predicted it may eventually dissipate entirely, though others believe it may stabilize at a smaller size. The storm's sustained nature is a consequence of Jupiter's size and the absence of a solid surface to create friction and dissipate energy. On Jupiter, storms can persist for centuries because there is nothing to stop them. The Great Red Spot rotates counterclockwise, like all anticyclones in Jupiter's southern hemisphere. Wind speeds within the spot can reach 640 kilometers per hour. The depth of the storm is not well known, but the Juno spacecraft, which began orbiting Jupiter in 2016, has revealed that the storm extends at least 300 to 500 kilometers below the cloud tops. The red color is thought to be caused by complex organic molecules or ammonium hydrosulfide or phosphine, products of chemical reactions occurring under the intense ultraviolet radiation of the sun and the convective mixing of the atmosphere, but the exact nature of the chromophores responsible for the color is not definitively established. The sun loses mass every second. Through the emission of light, the sun radiates approximately 3.8 times 10 to the power of 26 watts of energy. By Einstein's famous equation E equals mc squared, this energy corresponds to a mass of approximately 4.3 million tons per second. Over the sun's 4.6 billion year lifetime, it has lost approximately 0.03% of its original mass this way, a tiny fraction. The solar wind, the continuous stream of plasma emitted by the sun's corona, adds another approximately 5 million tons per second of mass loss. Over the sun's remaining lifetime of about 5 billion years, it will convert approximately 5% of its hydrogen into helium through fusion, losing a corresponding fraction of its mass to energy. Let your mind settle into stillness. The sun is burning steadily and patiently. 150 million kilometers away, it has been burning for 6 billion years and will continue burning for another 5 billion years. The light hitting your window tomorrow morning will have left the sun 8 minutes and 20 seconds before it arrives. You will never see the sun as it is right now. You will always see the sun as it was 8 minutes ago. This is the quiet reality of living in a finite universe where information travels at a finite speed. The pale blue dot. On February 14, 1990, the Voyager 1 spacecraft was commanded to turn its cameras back toward the inner solar system from a distance of about 6 billion kilometers. What it captured was a photograph of Earth as a tiny point of light, less than 1 pixel in size, suspended in a sunbeam against the black of space. Carl Sagan, who campaigned for the photograph to be taken and who wrote about it with extraordinary eloquence, described it as a mote of dust suspended in a sunbeam. Every human being who has ever lived, every king and peasant, every act of courage and cruelty, every inventor and explorer, every teacher and student, every saint and sinner, every moment of joy and suffering, and all of human history occurred on that pale blue dot. The photograph is not technically impressive. It is not the sharpest or most detailed image ever taken of any object, but it is perhaps the most philosophically significant photograph ever taken. It provides a visceral illustration of the scale of the universe and the smallness of Earth within it, not in numbers or abstractions, but in a single image. A planet reduced to a point of light, barely distinguishable from a photographic artifact, surrounded by the indifferent darkness of interstellar space. Space telescopes have given us windows into the universe that were impossible from the ground. The Hubble Space Telescope, launched in 1990 with a famously flawed mirror that was corrected by astronauts during a servicing mission in 1993, has operated for more than 3 decades and is among the most scientifically productive instruments in the history of astronomy. The Hubble Ultra Deep Field, a 11.3-day exposure of a tiny patch of sky in the constellation Fornax, revealed approximately 10,000 galaxies spanning the full range of cosmic history, including some of the most distant galaxies known at the time of observation. Each of those galaxies contains billions of stars. Each of those stars may have planets. The James Webb Space Telescope, launched on Christmas Day 2021 and operational since 2022, has extended humanity's reach into the early universe in ways that have already surprised and challenged the standard models of cosmology. Observing in the near and mid-infrared. GWEST can detect light from galaxies at redshifts greater than 10, corresponding to times when the universe was less than 500 million years old. The early results revealed galaxies that appear larger, more massive, and more structurally organized than the standard model of galaxy formation predicted they should be at such early epochs. The nature and significance of this discrepancy is an active area of investigation, and it may require revisions to our models of early star formation, feedback processes, or even the cosmological parameters themselves. Let your breathing slow to its most natural rhythm, not controlled breathing, not deliberate breathing. just the body doing what it does without any effort from you. The telescopes are collecting light right now. The photons are arriving from billions of years away. The data is accumulating photon by photon, and the detectors of instruments built by thousands of human beings working in collaboration across dozens of countries, speaking dozens of languages, united by curiosity about the same enormous darkness above all of them. The universe is approximately 13.8 billion years old, according to the best current measurements of the cosmic microwave background and the expansion rate of the universe. The observable universe, the region from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light years. The universe has expanded significantly since that light was emitted, which is why the observable radius is much larger than 13.8 billion light years. The total size of the universe beyond the observable horizon is unknown and possibly infinite, though the geometry of the observable universe is consistent with a flat or nearly flat spatial geometry. The fate of the universe depends critically on the nature of dark energy. If dark energy is indeed a cosmological constant, a fixed energy density of the vacuum, then the universe will continue to expand exponentially in the far future. The galaxies beyond our local group will eventually recede beyond our observable horizon, and the universe will become increasingly cold and dark. The stars will burn out over trillions of years. The stellar remnants, white dwarfs, and neutron stars and black holes will decay over even longer timescales, and the last black holes will evaporate through Hawking radiation, leaving a universe of cold, diffuse photons and elementary particles, expanding forever in an endless, silent, near absolute zero darkness. This is not a frightening future. It is an extraordinarily patient one. The universe has timescales available to it that make human history invisible. The sun's remaining lifetime of 5 billion years is 500 times the entire history of complex animal life on Earth. The universe's far future, measured in years with more zeros than you could write in a lifetime, is a canvas of almost unimaginable vastness. On that canvas, you are a brief and brilliant flash of consciousness, a temporary arrangement of atoms that can contemplate the whole. That is remarkable. That is perhaps the most remarkable thing in the universe. Let your body be heavy. Let your thoughts be gentle and slow. The universe is patient and dark and vast and full of extraordinary things. The stars are burning above you. The planets are in their orbits. The cosmic microwave background is arriving from every direction, the oldest light there is. The Voyager probes are drifting through the dark. The exoplanets are turning around their distant suns. The black holes are at the centers of galaxies, patient and enormous. And the cosmic web is drawing its filaments across billions of light years, the largest structure that exists. All of it is here, and all of it is real, and all of it will continue long after tonight is over. You are inside the most extraordinary place that exists, and tonight you are safe and warm and still, and the universe is keeping you company. There are still more facts the universe would like to share. The cosmos is patient and generous tonight. The interstellar medium is far more chemically complex than was imagined even a generation ago. Radio telescopes listening at precise microwave frequencies have detected the rotational emission lines of over 200 distinct molecules in the gas clouds between the stars. These include relatively simple molecules like carbon monoxide, hydrogen cyanide, and formaldehyde, but also startlingly complex ones, benzene rings, long carbon chains called polyions, sugars like glycolaldehyde, and amino acid precursors like aminoacetonitril. The large molecular cloud Sagittarius B2, located near the galactic center, has been found to contain ethyl formate, the molecule responsible for the flavor of raspberries and the smell of rum. If you could somehow inhale the interstellar medium of the galactic center, it would smell faintly of spirits and taste vaguely of raspberries. More seriously, the chemical complexity of the interstellar medium has profound implications for the origin of life, the building blocks of biology, the amino acids, sugars, and nucleobases that form proteins and nucleic acids form spontaneously in conditions common throughout the interstellar medium. Meteorites frequently contain amino acids, including several found in living organisms. The delivery of these molecules to young planetary surfaces by comets and asteroids during the early solar system may have provided a rich chemical starting point for the emergence of life. The universe has been practicing organic chemistry for billions of years in conditions far colder and more diffuse than any laboratory. Light echoes are one of the most visually spectacular phenomena associated with stellar explosions. When a star undergoes a nova or supernova, the brilliant flash of light it emits spreads outward in all directions. When this expanding light shell encounters a cloud of dust or gas that surrounds the star, the dust scatters some of the light back in the direction of Earth. Because the scattered light has traveled a longer path than the direct light, it arrives at Earth later. An observer watching the region around the explosion over months and years will see the flash of light appear to be expanding outward from the star's position in an expanding ring or arc, an echo of the original explosion replaying in slow motion long after the explosion itself has faded. Light echoes have allowed astronomers to reconstruct the three-dimensional geometry of dust clouds around stars, and to observe the evolution of supernova light curves in exquisite detail years after the original explosion. The V838 Monocerotis light echo is one of the most beautiful astronomical images ever taken. In 2002, a star about 20,000 light years away in the constellation Monoceros brightened dramatically over the course of several months, becoming among the most luminous stars in the Milky Way. As this outburst faded, Hubble images revealed an expanding light echo illuminating the complex geometry of surrounding dust shells and sheets, creating an ever-changing tapestry of illuminated structures that appeared to expand faster than light in the sky, though this superluminal appearance is a geometric illusion and does not violate relativity. Stellar spectroscopy, the analysis of the spectrum of light emitted by stars to determine their composition, temperature, and motion, is the foundation of modern astrophysics. It began with the observation by Joseph von Fraunhofer in 1814 that the spectrum of sunlight, when spread into its component colors by a prism, contained hundreds of dark lines at specific wavelengths. These lines, now called Fraunhofer lines, are produced by atoms in the sun's cooler outer atmosphere absorbing specific wavelengths of light from the hotter interior. Different elements absorb at different characteristic wavelengths, creating a unique spectral fingerprint. By the late 19th century, astronomers had identified dozens of elements in the Sun through their spectral lines, including helium, which was identified in the Sun's spectrum in 1868 before it was discovered on Earth. The word helium comes from Helios, the Greek sun god. The spectral analysis of starlight tells us not only what stars are made of, but also how fast they are moving toward or away from us. A star moving toward us will have its spectral lines shifted to shorter, bluer wavelengths, while a star moving away will have them shifted to longer, redder wavelengths, the Doppler effect applied to light. This technique has been used to measure the orbital velocities of stars and galaxies, revealing the presence of dark matter through flat rotation curves. It has been used to detect the wobble of stars caused by orbiting planets, leading to the discovery of hundreds of exoplanets. And it has been used to measure the recession velocities of distant galaxies, establishing the expansion of the universe. Venus, our nearest planetary neighbor and near twin in size and mass, is one of the most extreme environments in the solar system. Its surface temperature is about 465 degrees Celsius, hot enough to melt lead. Not because it is close to the sun, but because of a runaway greenhouse effect. The Venusian atmosphere is 96% carbon dioxide, creating a crushing atmospheric pressure at the surface 92 times that of Earth, equivalent to being 900 meters underwater. The greenhouse effect traps solar energy so effectively that Venus is hotter than Mercury, despite being nearly twice as far from the Sun. Venus rotates extremely slowly, taking 243 Earth days for one rotation, and it rotates retrograde in the opposite direction to most planets, so that the Sun rises in the west and sets in the east on Venus. The runaway greenhouse effect on Venus may have been triggered relatively recently in geological terms. Some models suggest Venus once had liquid water oceans and a climate somewhat similar to Earth's, but about 700 million years ago underwent a catastrophic resurfacing event that released enormous quantities of volcanic carbon dioxide. This may have triggered a positive feedback. More CO2 led to more warming, more volcanic outgassing, more warming, until the oceans evaporated and the hydrogen escaped to space. Venus today may be a possible portrait of what Earth could become if its atmospheric carbon dioxide were to increase dramatically over geological timescales. It is both a fascinating scientific object and a sobering warning. Uranus and Neptune are the ice giants, a distinct class of planet different from both the rocky terrestrial planets and the gas giants Jupiter and Saturn. Rather than being composed primarily of hydrogen and helium gas, Uranus and Neptune have mantles of water, methane, and ammonia, and a hot, dense fluid state called an ice. Despite this, their surfaces, the tops of their visible cloud layers, are extremely cold. Uranus's cloud tops are about minus 224 degrees Celsius, the coldest planetary surface in the solar system, colder even than Neptune, despite Neptune being twice as far from the Sun. This anomaly is one of the great mysteries of planetary science. Uranus appears to emit almost no internal heat, unlike Neptune. Jupiter and Saturn, which all emit significantly more heat than they receive from the Sun. Uranus also has the most extreme axial tilt of any planet in the solar system, rotating at 97.8 degrees from the plane of its orbit, meaning it essentially rotates on its side. As a result, its poles receive direct sunlight for 42-year periods, while the equatorial regions see the sun very low in the sky, followed by 42-year winters of complete darkness. During Voyager 2's flyby in 1986, Uranus's south pole was pointed almost directly at the sun. The cause of this extreme tilt is thought to be a giant impact early in the solar system's history, possibly from a protoplanet roughly the size of Earth that struck Uranus and tipped it over. Pluto's reclassification as a dwarf planet in 2006 was one of the most widely discussed decisions in the history of the International Astronomical Union. The trigger was the discovery of Eris in 2005, a body in the outer solar system that was initially thought to be larger than Pluto. If Pluto was a planet, Eris would also have to be a planet, and so would dozens of other Kuiper Belt objects of similar size. The EO defined a planet as an object that orbits the sun, has sufficient mass to be in hydrostatic equilibrium, meaning roughly spherical, and has cleared the neighborhood around its orbit of other debris. Pluto fails the third criterion. It shares its orbital region with thousands of Kuiper Belt objects. Pluto is now classified as a dwarf planet, a member of the trans-Neptunian population. The New Horizons spacecraft's flyby of Pluto in July 2015 revealed a world far more geologically active and diverse than expected. Pluto has a large, bright nitrogen ice-covered plain called Tombaugh Regio, informally the Heart, which shows no impact craters and therefore must be less than about 10 million years old, extremely young in planetary terms. It has a mountain range of water ice peaks rising 3,500 meters above the surrounding plains, towering as high as the Rocky Mountains. It has an extended atmosphere of nitrogen with complex photochemical haze layers, and it has Charon, its massive moon nearly half its own diameter, creating a true binary dwarf planet system where both bodies orbit their common center of mass, which lies in the space between them rather than inside either body. The Oort cloud is a vast spherical shell of cometary nuclei surrounding the solar system at distances of 2,000 to 200,000 astronomical units from the Sun. It is thought to contain trillions of icy bodies, the remnants of the early solar system scattered to extreme distances by gravitational interactions with the giant planets. The Oort cloud has never been directly observed. It is too far away and its individual members too small and dark to detect with current technology. Its existence is inferred from the orbits of long-period comets, which arrive from random directions in the sky on orbits that trace back to these extreme distances. When a long-period comet's orbit is disturbed by the gravitational pull of a passing star or the tidal force of the galactic disk, it can be deflected into the inner solar system, where it becomes visible for the first time as it warms in sunlight and sublimes gas and dust into a glowing coma and tail. Comets have been delivering material to the inner solar system throughout its history. The water in Earth's oceans, the organic molecules that seeded the chemistry of early life, and the dust that settles on your windowsill and on every surface exposed to the air, all contain components delivered by comets and asteroids over 4 billion years of bombardment. When you breathe, some fraction of the atoms in each breath have been part of a comet. The solar system's inventory of atoms is extraordinarily well mixed over geological and astronomical timescales. Let your breath be steady and slow. The Oort cloud is out there now, a vast cold sphere surrounding the solar system, its trillions of quiet bodies moving in their enormous year-long orbits. One of them, perhaps jostled by the gravity of a passing star, may already be on its way inward on a journey that will take it through the inner solar system in 1,000 years or 10,000 years, and it will appear briefly in Earth's sky as a fuzzy star with a glowing tail, just as comets have appeared throughout all of recorded human history, an omen interpreted by every civilization as significant, and in a sense, they are significant, just not in the way those civilizations imagined. The solar cycle is an approximately 11-year cycle of activity on the Sun, driven by changes in the Sun's magnetic field. During solar maximum, the Sun's surface is covered with many sunspots, dark regions produced by intense magnetic field concentration that inhibits convective heat flow from below. During solar minimum, the Sun is relatively quiescent with few sunspots. The cycle was first recognized in 1843 by the German amateur astronomer Heinrich Schwabe, who had spent 17 years counting sunspots. The Sun's magnetic field reverses polarity every 11 years, so the full magnetic cycle is actually 22 years. During solar maximum, the Sun produces more coronal mass ejections, powerful eruptions of magnetized plasma, and more intense solar flares, sudden bursts of electromagnetic radiation from regions of intense magnetic field activity. These events produce space weather, disturbances in the near-Earth space environment that can affect satellites, power grids, and radio communications. The current solar cycle 25, began in December 2019 and reached its maximum in 2024, producing intense geomagnetic storms and unusually widespread auroral displays that were visible at mid-latitudes around the world. Let your mind be still. The Sun is out there, cycling through its 11-year pattern of activity, its magnetic field threading through space and touching the Earth's magnetosphere. The planets are in their orbits. The comets are in their enormous ellipses. The interstellar medium is full of molecules. The galaxies are receding from each other in the expanding universe, and the universe is old and patient and filled with quiet, extraordinary facts that can fill a night of sleep with gentle wonder. All of it is here, and all of it is real, and all of it will continue long after tonight is over. You are inside the most extraordinary place that exists, and tonight you are safe and warm and still, and the universe is keeping you company. Sleep now. Good night.